In the previous video, we computed our first Fourier transform pairs, impulse functions, symmetric and antisymmetric impulse pairs, and the rectangular pulse-to-sinc relationship. Now we'll take the next step and answer a fundamental question. What is the connection between Fourier series coefficients and the Fourier transform? This relationship is powerful because it lets us use FT results to quickly find Fs coefficients and vice versa. We'll derive the key formula, work through an example with a periodic rectangular pulse, then explore how to find the Fourier transform of periodic signals using impulse functions. Finally, we'll compile a comprehensive table of Fourier transform pairs. Let's build the bridge between Fourier series and the Fourier transform. Consider a periodic signal x tilde of t with period capital T. We can construct it by periodically extending one period. X tilde of t equals the sum from m equals -infinity to infinity of x of t minus mt. Here, x of t is one period of x tilde of t. It equals x tilde of t for 0 less than or equal to t less than or equal to t and 0 otherwise. Now x of t is aperiodic, so it has a Fourier transform. X of omega equals the integral of x of t times e to the minus j omega t dt. Meanwhile, x tilde of t is periodic, so it has Fourier series coefficients x tilde of k. The key relationship connecting them is x tilde of k equals 1 over t times x of omega evaluated at omega equals k omega 0, where omega 0 equals 2 pi over t. In other words, the Fs coefficients are samples of the Fourier transform scaled by 1 over t taken at integer multiples of the fundamental frequency. Let's apply this to an example. Consider x tilde of t, a periodic rectangular pulse train with period t equals 4. Each period has amplitude 1 from t equals -1 to t equals +1. To find the Fs coefficients, we first identify one period. X of t is a rectangular pulse from -1 to +1. We already know its Fourier transform from the previous video. X of omega equals 2 over omega times sine of omega. Applying the key formula, x tilde of k equals 1 over t times x of omega at omega equals k omega 0. With t equals 4 and omega 0 equals 2 pi over 4, which is pi over 2, x tilde of k equals 1 over 4 times 2 sine of k pi over 2 divided by k pi over 2. This simplifies to 1/2 times sinc of k over 2. Notice how efficiently we found the Fs coefficients. Instead of evaluating the integral directly, we just sampled the Fourier transform that we already computed. Now let's consider the reverse direction. What is the Fourier transform of a periodic signal? A periodic signal x tilde of t can be written as its Fourier series. X tilde of t equals the sum over k of x tilde of k times e to the jk omega 0 t. Taking the Fourier transform of both sides and using the fact that the ft of e to the j omega 0 t is 2 pi, delta of omega minus omega 0, we get x of omega equals the sum over k of 2 pi x tilde of k times delta of omega minus k omega 0. This is a powerful result. The Fourier transform of a periodic signal is a train of impulses in the frequency domain, located at multiples of the fundamental frequency, with areas equal to 2 pi times the Fs coefficients. For example, cosine of omega 0 t has Fs coefficients 1/2 at k equals +1 and -1. Therefore, the ft of cosine omega 0 t equals pi times delta of omega minus omega 0 plus pi times delta of omega plus omega 0. Two impulses in the frequency domain at plus and minus omega 0. Let's summarize everything from this video and the entire Lecture 11 series. The key Fs to Ft relationship is x tilde of k equals 1 over t times x of k omega 0. Sampling the Ft at harmonic frequencies gives the Fs coefficients. In the reverse direction, the Ft of a periodic signal is x of omega equals the sum of 2 pi x tilde of k times delta of omega minus k omega 0. A train of frequency domain impulses. We also derived key Ft pairs across this lecture series. Delta of t transforms to 1. A shifted impulse transforms to a e to the minus j omega t0. A symmetric impulse pair gives 2 cosine omega t0. A rectangular pulse from minus t to t gives 2 over omega sine omega t. And cosine omega 0t transforms to pi delta of omega minus omega 0 plus pi delta of omega plus omega 0. These building blocks form the foundation for everything we'll study next in signal processing and system analysis.